A wave is one of nature's cleverest tricks, a way of moving energy from place to place without moving any matter along with it. Drop a stone in a pond and the ripple races outward, but the water itself just bobs up and down. Sound, light, the signal reaching your phone, all of it is waves carrying energy through. This unit builds in four moves. The properties that describe any wave, the single equation that links speed, frequency, and wavelength, the two great families of transverse and longitudinal waves, and the electromagnetic spectrum from radio to gamma. Let's start with the vocabulary every wave shares. Every wave is described by the same handful of quantities. The amplitude is the maximum displacement from the rest position, and it sets how much energy the wave carries. The wavelength is the distance for one complete cycle, from crest to crest. Together they give the shape of the wave frozen in space. Two more describe the wave in time. The period is how long one full cycle takes, and the frequency is how many cycles pass each second, measured in hertz. Frequency is simply 1 over the period, and the intensity, the power per unit area, is proportional to the amplitude squared, so doubling the amplitude quadruples the energy delivered. Now the single most important equation in the whole unit. The speed of a wave equals its frequency times its wavelength. It makes simple sense. Frequency is cycles per second, wavelength is the length of each cycle, so multiply them and you get length per second, which is speed. This one relation links the three headline quantities of any wave. There is a subtlety worth knowing. When a wave passes from one medium into another, say light entering glass, its speed changes, but its frequency stays fixed, set by the source. So it is the wavelength that adjusts to keep the equation balanced. Frequency is the wave's identity. Speed and wavelength bend to the medium. Waves come in two great families, defined by the direction of the wobble. In a transverse wave, the oscillation is at right angles to the direction of travel, like a wave on a rope or all of light. In a longitudinal wave, the oscillation is along the direction of travel, a pattern of compressions and rarefactions, like sound moving through air. One more idea, the phase, tells you where in its cycle a point is, measured as an angle. 2 points exactly in step are in phase, a whole number of cycles apart. 2 points exactly out of step, half a cycle apart, are in antiphase. Phase is the key that unlocks the next unit, where waves meet and combine. All electromagnetic waves, from radio to gamma rays, are the same kind of transverse wave, and they all travel at the speed of light in a vacuum, 3 times 10 to the 8 meters per second. What separates them is only their wavelength and frequency. Radio waves are long and low. Gamma rays are tiny and ferociously high in frequency. Finally, polarization, a property only transverse waves have. Normally, a wave wobbles in all directions at once. A polarizer only lets through the wobble in one plane. That is exactly how polarizing sunglasses cut glare. Crucially, sound cannot be polarized, which is the cleanest proof that sound is longitudinal while light is transverse. Here is the whole unit as one poster. Every wave has an amplitude, which sets the energy and gives intensity proportional to amplitude squared, plus a wavelength, period, and frequency, where frequency is 1 over the period. And the whole unit turns on one equation. Speed equals frequency times wavelength. Waves are transverse, wobbling across the travel like light, or longitudinal, wobbling along it like sound. All electromagnetic waves share the speed of light in a vacuum and differ only in wavelength. And only transverse waves can be polarized, which proves light is transverse and sound is not. And the boundary fence so you do not over-revise. What happens when two waves meet, interference and stationary waves, is the whole of the next unit. The detailed physics of how light diffracts and refracts and the quantum nature of light all come later. Here it is one wave, its properties, its equation, its type, and its spectrum.